All right, so today I want to talk about the Hardy-Weinberg equilibrium problems that you're going to see. Hardy-Weinberg is an equation that we can use to determine if a population is evolving, and you should be a little familiar with the formula by now. It is p squared plus 2pq plus q squared equals 1. And in case we're a little confused about what these variables mean, or if we're a little confused about some terminology, we got to think back to genetics. So in genetics, we should remember that if you are two big letters, you are considered homozygous dominant. That means that the dominant allele is expressed because that overpowers any recessive allele that is present. So in our equation, homozygous dominant, not the allele by itself, but just the fact that you're homozygous dominant is represented by p squared. Big A, little a, or as we call heterozygous, again, the dominant allele is present. It is going to mask the recessive allele. And in our equation, that is represented by 2pq. And finally, when you are two little letters, or homozygous recessive, that is the time, excuse me, when we will get to see that recessive allele show, because there's no dominant allele to mask it. And in our equation, it is represented by q squared. Now, I have only gone over genotypes. I have determined p squared, 2pq, and q squared. Those are genotypes. When we're talking about individual alleles present, so the presence of having an A, a big A, or a little a dominant or recessive allele only, we represent that as p and q. These are just the alleles. And the other equation that you should be familiar with, besides the Hardy-Weinberg equilibrium equation, should be p plus q. P plus q equals 1. Not entirely sure what's happening here. Maybe it wants a different color. P plus q equals 1. So if you were going to memorize anything for Hardy-Weinberg, it should be these two equations. However, on the AP test, those equations will be available to you on the formula sheet. So let's practice some Hardy-Weinberg questions. They do require a calculator. They also might require you to apply chi-square analysis. And I know how much we love doing chi-square analysis. That's going to come back today. So let's look at our first question. The frequency of two alleles in a gene pool is 0.19 and 0.81. Assume that the population is in Hardy-Weinberg equilibrium. Calculate the percentage of heterozygous individuals in the population and calculate the percentage of homozygous recessive in the population. So I like this question because it gives me numbers already. It gives me big A and it gives me little a. Again, this is the frequency of just the dominant allele and the frequency of just the recessive allele. It is not telling you the frequency of being homozygous dominant, and it is not telling you the frequency of being heterozygous, and it is not telling you the frequency of being homozygous recessive. It is just telling you the frequency of the dominant allele and the frequency of the recessive allele. So big A is P and little a is Q. Now, according to the Hardy-Weinberg equilibrium equation, that p squared plus 2pq plus q squared equals 1, heterozygotes are represented by 2pq. Therefore, the number of heterozygous individuals or big A, little a, because that's what it's asking for, is going to be equal to 2pq. Well, lucky for you, they gave you P and they gave you Q. So all you have to do is plug it in. 2 times P, which is 0.19, Q, which is 0.81, and then you do some math, multiply them together, and you should get 0.31. Now, it is not asking you what is the fraction or what is the number or what is the decimal. It is asking you what is the percentage of being heterozygous. So when we do the math, we get 0.31, which is equal to 31%. So the percentage of being a heterozygote in this population should be 31%. Now we're not done because it also wanted us to calculate the percentage of being homozygous recessive in the population. Now to be homozygous recessive, you should be little a, little a. And that is represented by q squared in our equation up here. So to calculate the percentage of being homozygous recessive, we're going to plug in that q value of 0.81 and square it. And we're going to get, again, we're going to get a decimal. That's going to be 0.656 or 0.66, which translates to being 66%. So the percentage of homozygous recessives in this population is 66%. The percentage of heterozygote individuals in the population is 31%. And if it wanted us to know the percent of homozygous dominant in this population, we would just find p squared, which would be 0.19 squared. All right, so let's keep moving forward with more questions. I want you to be exposed to as many ways that Hardy-Weinberg questions can be asked as possible. When you see the AP test, they could be multiple choice questions where you have to calculate the percentages and you have to calculate values and find them in the multiple choice question. Those are the fun ones because you can eliminate dumb answers. Sometimes you'll see them as gridables where you're given the question and all you have to do is do the math, and then you have to literally put the number in and then bubble the number. So you don't have any information to go off of in the answer choices and eliminate dumb answers. So you need to know what you're doing. There's been about 3 or 4 that have been asked since 2012. And then of course, you know, if you are the unlucky year that you get a if you get a Hardy-Weinberg equation for your response where you have to write about it, you want to know what you're doing. So let's go forward with some more examples. So 2, an allele for white wool, and notice it's capital, so it's dominant. It's dominant over the little w allele for black wool. So white is your dominant, and black is recessive. Again, I hate when they use W's because they look the exact same capital and the exact same lowercase. So be cautious when you're writing. In a sample of 900 sheep, 891 are white and 9 are black. Calculate the allelic frequency within the population, assuming that the population is in Hardy-Weinberg equilibrium. Now, luckily, they tell us it's Hardy-Weinberg equilibrium. I know what equations I need to be using. It would suck if they gave me something that I had to go and read through the information it gave me to figure out, is this in Hardy-Weinberg equilibrium? But luckily, it just gives it to you most of the time. So we are here to calculate the allelic frequencies. So we are calculating, so the allelic frequency, we are calculating P, and we want to know Q. That's what we're looking for here. We're not looking for P squared, not looking for 2PQ, we're not looking for Q squared. Those are genotypes. We are looking for allelic frequencies. So let's go through and figure out what's going on. So remember, the P is the dominant. So in this case, it's capital W. That's the dominant allele. And Q represents your recessive allele, represented by little w. To calculate the value of Q, we need to realize that it's telling us there are 9 black sheep. So 9 of those sheep are showing the recessive phenotype. And in order to do that, you need 2 recessive alleles. So these black sheep, these 9 black sheep, they must be little w, little w. And according to our equation, homozygous recessive is my Q squared term. Now, don't start to think that 9 is Q squared. It's not. You need to find the frequency. So we need to take the number of individuals and we need to divide it by the total individuals in the population in order to find Q squared. So there were 9 sheep that are black. There are 900 total sheep, and I need to get that number, so that's 0.01. So that is going to be Q squared. So Q squared is 0.01. That is the frequency of homozygous recessive individuals. Notice I'm not saying the frequency of the recessive allele. I'm not saying that. I'm saying the frequency of being homozygous recessive. So I have to get the number of homozygous recessive individuals, which in this case was my 9 black sheep. I had to divide it by the total number of sheep, 900, to get my Q squared. Okay, so now I have Q squared. I can get some information off of that. Now remember, at the very beginning, I said that P plus Q is going to be equal to 1. I've got Q squared here, so I can get Q now. So to get Q, I have to square root 0.01, and that gives me 0.1. So Q is 0.1. So I'm halfway done. Remember, I was trying to find out the value of P and the value of Q. I now have Q. It is 0.1, so I'm going to write it over here. Whoop, not P. Q equals 0.1. Now I can find the frequency of the dominant allele. So P plus Q is 1. So P plus 0.1 should be equal to 1. So now it's an algebra problem. 1 minus 0.1 equals 0.9. So my P value is 0.9. I'm done. I've got my frequency of the dominant allele. It's 0.09. And the frequency of the recessive allele, it is 0.1. So this one looked like it was going to be complicated. It wasn't. You need to read what it wants to know about. So this one wanted to know the allelic frequencies within this population. Number 1 wanted to know the heterozygous individuals, and it wanted to know the homozygous recessive individuals. So you can find Q squared, and you can find P squared, and you can find 2PQ, but make sure that when you're bubbling or you're boxing in answers, you're writing your free response, that you address what the question wanted to know. If you would have put that Q squared is 0.01 and boxed it or bubbled it, you'd be wrong, because that's not what it wanted to know about. So let's keep going. Number 3, in a population that is in Hardy-Weinberg equilibrium, the frequency of the recessive homozygote genotype of a certain trait is 0.09. Calculate the percentage of individuals homozygous for the dominant allele. Okay, it is telling you the frequency of the recessive homozygote genotype. It is telling you Q squared. Q squared is 0.09. 9. We got Q squared. But it wants to know the percentage of homozygous dominant alleles. So we're going to have to do some math. I've got Q squared. From this, I can now get Q, and I can get P. So to get Q, I have to take the square root of 0.09, and that is 0.30. So I've got Q squared here. I've got Q, and just to reiterate, Q squared is my homozygous recessives. Q is just the recessive allele. Now I can find P, the dominant allele. So P plus Q equals 1. P plus 0.3 equals 1. So 1 minus 0.3 is going to be 0.7. So that is P. That is your dominant allele. But that's not what the question wants to know about. It wants to know what is the percentage of individuals that are homozygous dominant. It wants to know P squared. So to find P squared, we're going to take 0.7 and square it, and we're going to get that P squared is equal to 0.49 or 49%, because I wanted to know percentage. 49% of this population will be homozygous dominant. All right, let's keep it moving with number 4. In a population that is in Hardy-Weinberg equilibrium, 38% of the individuals are recessive homozygotes for a certain trait. In a population of 14,500, calculate the number of homozygous dominant individuals and heterozygous individuals. So this one's different. We're not calculating percentages. They want to know how many individuals in this population are homozygous dominant and how many are heterozygous individuals. So it doesn't want to know what's the percent of being heterozygous. It wants to know how many specifically. If I were to count out in this population of 14,500, how many are going to be homozygous dominant and how many are going to be heterozygous? Well, right now it gives you the 38% of individuals are recessive homozygotes for a certain trait. It is giving you Q squared right now. So Q squared is 38% or 0.38. So to find Q, you have to take the square root of 0.38, and you are going to get 0.616. That is your Q value. Again, Q squared, homozygous recessive. Q, just the recessive alleles. Now you can go through and you can find P. So P plus Q equal to 1. You've got Q. P plus 0.616 is equal to 1. When you do the math, you should get that P is equal to 0.384. P squared is 0.384 squared. So P squared is going to be equal to 0.147. Okay, so I've got P, I've got Q, I've got Q squared, I've got P squared, I've got all the information I need to solve this problem now. So let's start with part 1 of what it wants to know. It wants to know the homozygous dominant individuals. So what we're going to do is we're going to take P squared and we're going to multiply it by the total population number. And we will get the number of homozygous dominant individuals. So P squared was 0.147. Our total population was 14,500. When we do the math, we're going to get 2,132 individuals. That is how many people when I count it out, should be homozygous dominant. Now let's find the number of heterozygous individuals. To find that one, we're going to take 2PQ and multiply it by the total population number, and that'll give us our number of heterozygous individuals. So 2PQ, 2, our p-value was 0.384, Q was 0.616, our total population was 14,500, and when I break down that math, I'm going to get 6,859. So the number of heterozygous individuals in this population is 6,859. And if we wanted to double check our answers, we could get the number of homozygous recessive individuals, add it all together, and make sure that that is close to 14,500. If it's 14,501 or 14,499, it's close. If it's 17,000, it's way off and something was wrong. Let's go to 5. Allele T for the ability to taste a particular chemical is dominant over allele little t for the inability to taste the chemical. 400 university students were surveyed and 64 were found to be non-tasters. Calculate the percentage of heterozygous students. Assume that the population's in Hardy-Weinberg equilibrium. So 64 of these kids were non-tasters. That means that they were homozygous recessive. So the number of homozygous recessive individuals was 64. Okay, that is not Q squared. To find Q squared, you need to take the number of homozygous recessive individuals and divide it by the total number in the population. So that would be 64 divided by 400. So Q squared is going to be equal, well, that's a weird way to represent that. Let's try that again. 64 out of 400. It's going to be Q squared. So when we do the math, that's going to be 0.16 or 16%. That is the Q squared number. To find Q, because remember, Q squared is just the frequency of homozygous recessive individuals. I want to find the frequency of the recessive allele here. So Q is going to be the square root of 0.16, and that is going to equal 0.40. Now, let's get let's get P. Remember, P plus Q is equal to 1. P plus 0.4 equal to 1. Therefore, P is going to be 1 minus 0.4. So P is going to be equal to 0.6. Let's go ahead and get P squared just for funsies. P squared is going to be 0.6 squared. So that's going to be 0.36. Got that? Okay. Now, it wants to know the percentage of heterozygous students. It wants to know 2PQ. So let's plug in some numbers. 2PQ. 2P was 0.6. Q was 0.4. Calculate it out, and we're going to get 0.48, but it wants to know percentage, or 48% would be heterozygous. Easy. Well, okay, let's go to number 6. In humans, Rh factor genetic information is inherited from our parents, but it is inherited independently of A, B, O blood type alleles. In humans, Rh plus individuals have the Rh antigen on their red blood cells, while Rh negative individuals do not. There are two different alleles for the Rh factor known as Rh plus and Rh. Assume the dominant gene, Rh, produces the Rh plus phenotype, and the recessive Rh allele produces Rh negative phenotype. In a population that is in Hardy-Weinberg equilibrium, 160 out of 200 individuals are Rh plus. Calculate the frequencies of both alleles. So we are calculating P and we are calculating Q. So let's start with our homozygous recessive percentage, or our Q squared. So 160 of our 200 individuals are Rh plus. Oh, jumping the gun here. So that means that 40 are going to be Rh negative. So Rh negative was our recessive genotype. So to find our Q squared, we have to take the 40, divide it by 200, and that gives us 0.2. So that is the frequency of being homozygous recessive. Now let's calculate the recessive allele. So Q is going to be the square root of 0.2, and that is going to be 0.45. Again, P plus Q is equal to 1. So P is going to be 1 minus 0.45. So that is going to be equal to 0.55. So as the frequency of the dominant allele, P squared, 0.55 squared, is going to be equal to whatever that number is. We don't really need it here. Okay, now we want to know what is the frequency of both alleles. So the frequency of Rh plus, that is our dominant allele, or P, is going to be equal to 0.55. The frequency of the Rh negative, or the Rh, all lowercase letters, let me fix it so it's consistent. Rh, oh my gosh. Rh, or my Q allele, is going to be 0.45.